Welcome to Chapter 3B. In this segment, we'll explore the peptide map, a powerful visualization tool that lets you view uptake data across your protein sequence. You'll learn how to customize the display, highlight meaningful patterns, and use the Localized Uptake Solver to dig deeper into structural insights. Let's get started.
Another useful visualization is the peptide map. The peptide map is going to show the peptides that have been measured and have passed all the filters onto the protein sequence. The color of the peptides is going to be the deuteration value for each peptide. When you open this tab initially, it'll have one of the proteins selected, usually either the protein in your project or the first protein in your project. It'll have all of the labeling time points shown all at once. This is visualized with a gradient that you can see on each bar. It's a little hard to see when the bars are small, but if I make the bars a little bigger, you can see that each bar is actually split into sub-bars that represent each time point. To just view a single time point, simply select one of the time points in the labeling drop-down menu. The initial condition that is shown is going to be a target versus the control state in the case where you have a control state set, or it's going to be the first protein state in your project compared to nothing, basically by itself, where the color will range from the values will range from 0 to 100%, and the color will be the total deuterium uptake that a peptide has in that single state. When a control state is set, then as you've seen before, the values are going to be the delta deuteration for each peptide, where blue means protection and red means deprotection. The colors on the peptide map are all customizable. You can just select a different color from this drop-down menu, and you can even select a custom color or a custom color code. These colors can be set to really anything, including transparent colors. Once you set a color, every export will contain that color for this view. To export this view, you can select the Save Image button, which will convert this view to a high DPI image saved on your computer. By default, this format's going to be .tiff, but you can select any different image format that you prefer. Other than colors, you can customize the bar height just as I've done before. I just made it bigger, but now I can make it a little smaller. I can tell it whether it should have equal spacing. This just means when the stacks are really large, the protein sequence will be spaced equally between each row. We can show the title, we can show the legend. You can mark areas that have no coverage in gray. This is enabled by default just so that it stands out a little easier. You can also set a custom title for this view. As you can see, it'll have a few stats shown by default. For example, the sequence coverage, the peptide length, and redundancy. But if I wanted to set a custom title for this, I can just type that into the title text box here. So for example, this is a custom title. And you can do this before you export the image if you wanted to customize it. The next feature I would like to show in this view is going to be the Localized Uptake Solver. I just set the color back to blue just because it corresponds a little better with the protection versus deprotection color scheme. The feature that I wanted to mention is this Localized Uptake Solver. This Uptake Solver is a drop-down menu that allows you to select different solving algorithms for reducing the overlapped peptide deuteration into independent, even residue level segments on the protein sequence. So to show you, I'm just going to select one of the options. And now I'll just kind of cover, I'll just mention that the options here are described in the documentation, and they come from certain different ways of doing this in the literature. And one way is the Babbage and Smith matrix algebra. Another way is by using a weighted average described by Keppel and Weiss. The NNLS one is a non-negative least squares method of solving it, which exists in the original HD examiner. That is the method that the heat map from the original HD examiner is generated. There's not a big difference between the Babbage and Smith method and NNLS method. They both pretty much do the same thing. They'll get converging values for most of the peptide segments, for most of the protein segments. So how does it actually calculate the deuterium incorporation on each segment here? Well, just like in the original HD examiner, the first thing it'll do is it'll draw peptide boundaries for each peptide. We usually ignore the first two residues of the peptide just because the back exchange in that zone is really fast, so it doesn't really hold on to deuteration really well. This setting will be covered in the parameters a bit later, but you can override this setting so that you only emit the first residue, for example. So after each peptide start and stop is mapped, you then get these segments on the protein sequence. And then what we do is we try to assign uptake values to each of these segments so that these uptake values can then be summed back to the original peptide deuteration. So we compare the assigned uptake for these segments to the original measured peptide deuteration to then generate an average error. And this error is displayed as the confidence color above these bars. It ranges from green, which is high confidence, to red, which is low confidence. Regions that are low confidence simply mean that the reconstructed peptide deuteration from each of these independent segments doesn't quite match really well to the originally measured peptide deuteration. And so regions that are marked in orange or dark red should be taken with a grain of salt just because that region is a little harder to solve. And there could be many reasons for this. There could be outlier peptides causing issues, or there could be actual disagreements between the peptides in this region, and that needs to be resolved. So for example, in this tag here, it seems one peptide stands out as an outlier, that the deuteration doesn't quite match the rest of its neighbors. So one thing you can do is simply just remove outlier peptides if you want. And once you remove an outlier peptide, you will see that the confidence in that region will change. And in this case, it got better because that peptide was a bit of an outlier. The rest of the peptides agreed more on this deuteration assignment than what was before. Areas of the sequence that are marked black mean that in this zone there may potentially be multiple solutions to these segments, potentially infinite solution depending on how many segments you have. So the algorithm, instead of just giving one solution, it'll actually just say it's unsolvable.
That wraps up our tour of the peptide map. Up next in Chapter 3C, we'll explore the State Comparison tab, where you can directly compare experimental conditions and highlight significant differences in uptake. Let's continue.